you very much. Hello, dear colleagues. My name is Moghadam. I think you should have my voice, but let me check myself. Yes, okay. So it seems should be okay. I should thank Dr. Ghosh, Dr. Raqib, Mr. Hilali, Mr. Ali Khan, Mr. Shahid Ala, and our dear colleagues in S8 component of the project. Also, I should thank Mr. Rudra for his nice coordinations and our dear colleagues in the Engineering Staff College of Bangladesh. They have done lots of work for hosting the program. Yesterday, we had started some talk about the existing building and trying to understand that if for the existing buildings we need a new procedure or procedures, or it's not a big change in the way that we handle the design for the new buildings. With some modification, we do that for the existing buildings. We reviewed that how's the design approach for ordinary loads, and remember that for the ordinary loads, we design for a strength. So the force, the strength of the elements are assigned such a way that be more than the demand for that response parameters in each element. But then for the extraordinary loading such as blast, and in our case for the earthquake, we in cases that the level of load is much more than the other loads, we accept damage. There is no way that to design economically for such a large forces. So we accept damage and we design for ductility. For the ordinary loads, we design for strength. Of course, we check for the stiffness, but we design for strength. And the seismic design, we design for damage, design for ductility. Ductility is damage. So when we look at the design procedure in BMBC for the seismic design of new buildings, we saw that the main point is the R factor, because for the new buildings, we have control that how the elements, how good supervision in the field, that detailing can be applied and implemented in the building. So it is possible that we reduce all the forces that is expected to be applied by earthquake to the building for a specific level by a R factor, because by ensuring the implementation of those detailing, we can be sure that the ductility that is provided in the building is more than the damage that is expected. So the ductility capacity is more than ductility demand for that earthquake. We call this approach for the seismic design based on ductility. Then for the coming to the evaluation of the existing buildings, we again review that there are many approaches for the evaluation of the seismic evaluation of the existing buildings. but we focus on the most detailed one, systematic evaluation, or sometimes they call it in some other references DEA, detailed engineering analysis. The way that we can check the building for different level of earthquake hazard and check that if specific performance levels are satisfied or not. Today, as was mentioned by dear Mr. Woodrow, we try to see if the approach that we are familiar, we are as a structural engineers, structural designers, we are familiar with the linear elastic approach, with the softwares that model the buildings linear elastically. Can we use that for the seismic evaluation of the existing buildings or not? Yesterday I mentioned that some codes they just accept for the systematic approach, they just accept nonlinear inelastic modeling. But in many other codes, they accept both linear and nonlinear. But how we can use linear approach that is more easy, more familiar for us for the evaluation. As we can expect, again for evaluation, there are two components that we should try to find. One is the demand, one is the capacity. And the design problem is you check that for that specific demand, the capacity that is provided is more. So we talk many different concepts, many different aspects, many different, we mention many different names, but at the end, everything either related to capacity evaluation or in the demand evaluation for a existing building. No, we just look at the existing. And in our approaches, mainly the problem is the calculation of the demands. As we see later in the linear analysis and on Tuesday for nonlinear analysis, that the capacity is simpler. And we, for the capacity calculation, we use the formulations that we already have. So it's not that much difficulty, that much new concepts. But for the demand, mainly, we have the new approaches. So, regarding the different analytical methods, some existing building codes accept all of the linear and non-linear approaches. Of course, for each of them, they provide some limitation. If those requirements are satisfied, we can use them. And the terminology usually we use linear and the linear approach or non-linear approach, and the criteria that usually is important that we use linear or non-linear is the level of irregularity in strength. We can later we see different measures, but generally, in a general sense, the strength. If the strength in the building is distributed irregularly, it's better to use none. So the differentiation between linear and nonlinear is mainly based on strength. Then for linear can be a static analysis or dynamic analysis. For nonlinear can be again a static nonlinear or dynamic. Performing static or dynamic is mainly governed by the level of irregularity, not in the strength, but mainly on stiffness and mass. So if we have a building with many irregularity with respect to mass and stiffness, it's better to do dynamic, either linear dynamic or non-linear. If we have a building with lots of strength irregularity, better to do non-linear in a very general sense. Then for the static methods, in most of the codes for the evaluation of existing buildings, they use seismic coefficient method, but also the capacity spectrum method, which is also widely being used in both codes and softwares. But the seismic coefficient method is more acceptable, and today we will go through this approach. For dynamic approach, we have response spectrum, or very nice and very advanced and simple approach, or time history analysis that at the end of today's talk, we talk that why this time history analysis that is more similar to the earthquake event, to the phenomena, but is not till now being used as much as, for example, the pushover analysis or static analysis that are not basically very similar to the behavior of the building during earthquake, which is dynamic time history analysis. Is not that similar, but why we don't, little by little, the codes are going toward the using time history analysis more and more, but why till now that happened, we will discuss at the very end of today's talk. So there are lots of methods to be used. We mentioned about the limitation for linear procedures, when we can apply linear procedures. In very general sense, I said when the strength is regular, it's better we can use linear. But if the building is very irregular in strength, then it is better to use non-linear. But more detailed articles is like this. First of all, before going through the articles one by one, in general, in the linear analysis, if you want to have a measure, an index of the damage, because everything is linear, if you, and the superposition is valid. Therefore, so if we increase the load twice, because superposition is valid, every response will be multiplied by 2. If we multiply the force by 3, applied force, earthquake force, for example, by 3, all the responses due to the earthquake will increase 3 times. So, but we don't get damage in the building the way that really in the building during earthquake will happen. So the measure of damage, the measure of non-linear behavior in the linear analysis is DCR, demand capacity ratio. Demand capacity ratio. The terms are maybe is not that familiar, but little by little becomes more familiar. Demand usually the U shows the demand in the value of parameters, and the capacity is mentioned by C as a capacity. And for the demand, you see that we just look at the deformation control parameters, because one of the basic concepts in the seismic design is that when we look at a building, and this building is being designed for to get damage in the earthquake, the design philosophy for the new building is that we design such a way by distributing the strength such a way that the damages happen at specific points. So based on the experiments, based on the previous earthquakes, the behavior of the elements, we have some experience that, for example, in a beam element, which response parameter is more ductile. If we test the ordinary reinforced concrete beam, we say that it in the bending it behaves more, for example, ductile, because when the longitudinal reinforcement is yielded, then if the detailing is good, we can have a good plastic deformation before the concrete crashes and the failure happens. So we try to, by design, by implementing design articles, to concentrate the damages, for example, in B. If the bending is in that element more ductile. For concrete, usually we are scared of the shear, so we don't focus on the shear as a ductile behavior or on torsion or our axial behavior. So the first concept that we had in the existing buildings, and we talked about that a little yesterday, is we divide all the responses to deformation control or force control response parameters, ductile ones or brittle ones. The concept is the same as designing a new building, but in the new building, because we use mainly prescriptive approach, so we don't really approach to this wording, but it's the same approach. Usually we say that in the earthquake, we design the buildings that some location get damaged, or fuse, and then that controls the amount of the force that will transfer to the more brittle part of the building. So when we look at a building from the seismic design point of view, we see that there are some elements, and in each element there are response parameters under force, shear, bending, torsion, axial load, and some of them we assume as the ductile parameters. We can accept some level of plastic deformation, some level of damage in them. And there are some other response parameters, depend on the system and material, that they are brittle. So we call them force control parameters. And here you see that whatever we are talking about damage, demand to capacity ratio, that we accept that the level of load passes the capacity is just for deformation controllers. We don't accept any DCR more than one for the force control. Therefore, the easiest way that in the linear analysis, we know that if the building get damaged or not, we go to the elements, look at the, or estimate the level of the responses for the different response parameters. For all force control responses should be less than one. If is more than one, the building is collapsed. And the load pad, one load pad is failed. But for the deformation control parameters, we accept, we estimate this value, and then we check this value with the acceptance criteria for that performance level. For example, we find that in this beam, the DCR for the bending is 3. Means that the demand is 3 times the capacity. The capacity for the deformation control parameters will calculate it by using a expected value for the material properties. Because again, yesterday talked that we complicate the approach to be as economical as possible. So for every material that we have in the elements, we use 2 values for the as a characteristic of that material. One we call it expected strength. One is lower bound strength. Expected is the mean of the values of, for example, if you have done a few tests on the material, the mean value is expected value for the strength of concrete, and the mean minus 1 standard deviation is a lower one. For the force control, response parameter, for scary response parameters, the ones that are very brittle, we use capacity of L, lower one. But for the deformation control parameters, we use the expected value for the characteristic of the material. Therefore, for the calculation of the capacity, we usually in the evaluation codes, new formulation are not introduced. We use the same equation that we have for calculation of the bending strength of beam. But the value for material, for Fy, F prime C, those will be for the deformation control parameters will be expected value. For the force control parameters, it will be lower. Therefore, this is a good measure of the damage in the deformation control parameters, because we just accept damage there. Therefore, here, where the linear procedures are acceptable, it depends on if really building gets that much damage. If the building is not that much damage, so the linear approach is good. It depends on this. Also on the strength irregularities. It's not soft story irregularity. It's weak story irregularity. It's not a irregularity in stiffness, irregularity in strength, or is not torsional stiffness irregularity, torsional strength irregularity. Yeah. Therefore, to have a general sense, the concepts are more important. We don't want to go to the details. These articles changes from one version of code to another, but in general sense, the linear approach, they're okay when we don't have mainly strength irregularity. And if we have strength irregularity, still maybe we be able to use the linear analysis if the level of damage is not that much. If either this or this exists, and if a component DCR is the lesser of this, then you should go non-linear. So just have a general overview. We can use linear procedures when the strength irregularities are not there, or the amount of damage is not too much. Sometimes they put a threshold of 2, sometimes they put a threshold of 3, depend on the different codes and the level of conservatism. Okay. Then for the linear, static and dynamic, as I mentioned, in general sense, if there is a irregularity in stiffness or mass, is better to do dynamic analysis. Linear, non-linear, depend on strength irregularity. Static or dynamic depend on mass and stiffness irregularity. You can see is talking about period. Period is a stiffness and mass. It talks about the not torsional strength anymore. Torsional stiffness, vertical stiffness, all the things that are mainly deals with the irregularity in stiffness or mass. Therefore, we don't need to go to details in general concepts. For linear, non-linear strength is important. For the dynamic and static, stiffness and mass. So for 2 days discussion, we look at the steps in the linear analysis procedure, which these are exactly those steps in a way. The limitations, we have some talk about that. Then we introduce the main item here, which was the estimation of the, as I mentioned, estimation of the demands. So the estimation of the base shear for an existing building under a specific level of earthquake will be introduced. And because the approach is linear and is not consistent with the event, the event is earthquake, building will get damaged. So really the behavior is non-linear, inelastic. And so naturally we should somehow adjust the demands that we get from the linear analysis. So we discussed that what kind of adjustment we should do for the deformation control parameters, what kind of adjustment we should do for the force control parameters. So the results from the linear analysis be a good estimation of the real inelastic behavior. So let's go and see. Let's start usually for the systematic evaluation is from the performance objective. for the systematic approach, both in the elastic or inelastic, for dynamic or static. Always we start from either the code, decide that what performance objective should be used. But in general, the importance, the advantage of the performance based is that you have the freedom to, or you say client has the freedom to select what performance objective that they want, and we have the tools to check whatever they want. It's not like a provisions in the design of new buildings that everything is set for a specific level of earthquake and a specific level of performance. So that's fixed. But here in performance based, no, you can have different level of earthquakes and even select something else. Here there is 4 levels mentioned, but whatever we want. And then we have the tools to check the demands for that level of the earthquake and see if these demands satisfy the requirement for that specific performance, building performance level or not. Therefore, for example, they say that please check this building, if this building is this existing building, is satisfying the life safety performance level under this level of earthquake. And so they start is with the selection of the performance objective. What level of the hazard and what level of the performance. We start from this. Now the demand part is here. The demand part is we need just a formula that we transfer the level of earthquake to a level of force that should be applied to building, to the base shear. So we need a formula to give us base shear, exactly the same approach that we have for design of new buildings. Then we apply this base shear distributed to the building and look at the different demands for the force control parameters, displacement control parameters. We adjust them to somehow modify because our methodology is linear, but the real behavior is non-linear. And then we check with the acceptance criteria. Acceptance criteria for the linear analysis will be, this acceptance criteria will be that for force control elements, none of the force control parameters should exceed the lower level strength of the M. Lower level strength. The formula for example, shear capacity of this beam, but for the material properties, we will put the lower bound characteristics for the concrete and steel if it's reinforced concrete. Then for the deformation control ones, we accept that the demand be more than capacity. The level of the increase is mentioned based on the condition of the element and the performance level. Very nice, very important, as we will see later. Therefore, now our assignment is fixed. What we need here, just how to transfer the earthquake hazard to a base shear. And that's it. That's the formula, and because of that, is coefficient method because it has coefficients. So for the design of the new building, we already discussed yesterday that we calculate base shear, and we design the building for that base shear based on the second law of Newton. So just we need to estimate that level of earthquake, what maximum acceleration will introduce in the building, and multiply that by mass or weight of the building and find the base shear. But this is a big value, so we accept that based on the detailing that is possible for you, you check that in your site, construction site, is it possible for you to do much more details, advanced details, use bigger bar. If it's not possible, use a smaller bar. So, because you use all those requirements, you know that for the building, you can reduce all the demand by one. But for the existing buildings, if you want to use the R value in the new building, that's very dangerous because those detailings are not there in the existing building. This R has a list of detailing requirements, which is not there for the existing buildings. Or if we calculate a specific R, that will be corresponding to the weakest, the most deficient response parameter, so it's not economical. Instead, we forget about it. Our formula for the coefficient method for existing buildings give us the best estimation for base shear that will be produced, but that level of earthquake. So now, seems very simple. Seems very simple. If you look at the components of the formula, then what will happen to that R in our approach for the existing buildings? We have it, what we call it N here. The difference is we have for the whole building in the new buildings 1 R, but here for each element we have different N, because for in existing buildings some elements can be well detailed, some are not well detailed. So if you want to use 1 R, it will be based on the worst element. So this way is not economical at all. And therefore, yeah, instead of dividing the whole demand by R, we calculate demand completely. Instead of dividing the demand, we multiply the capacity. So the R that is usually here, bottom here, now comes here and multiplied by to the capacity instead of reducing the demand. So for the deformation control parameters, force control parameters, they shouldn't get damaged. For the deformation control parameters, we accept that their capacity be less than demand. Capacity less than demand, and they get damaged. But we accept if the condition of that element give us a M value that when you multiply by the capacity, exceed the demand. Itself is less, but by this R value, element-based R value, not system-based R value. Also, if our information regarding the building is less, we may reduce. If our information, if our knowledge about the building is good enough, we use, for example, value 1. If our knowledge is less, maybe we use 0.9. So that gives us a flexibility that the engineer decides, the owner decides, that wants to do lots of testing in the building or do less testing and less knowledge factor. But we will talk about that later. Yeah. So the general approach will be that we calculate the base shear for that specific level of earthquake. Then we will apply that to the building. We expect that all force control elements, their demand be less than their capacity, lower bound capacity. But for the deformation control parameters, they are okay if they are less. If when they multiply by M, that this is shows the level of ductility that a specific element, these specific parameters, for example, in bending, has, and for every performance level, for that specific element, we have a special M. So we have one M for IO, one M for LS, one M for CP. So M depends on the condition of element. Very nice. Good elements have bigger M. Bad elements have lower M in the same building. But at the same time, for that specific element, the M for IO is less, M, because in a way, M shows the acceptable level of damage. So for the IO, we accept less, for LS more, for CP more. So, yeah, general sense, we don't want to go to detail of this. For now, this is important for us. Forget about this for now. Just to make a connection where the R value goes, R value will return somehow in future. But for now, we want to focus on this formula. So, first of all, we want to calculate the base shear under earthquake. Where is earthquake? Where is earthquake in our formula? The earthquake is in SA, is a spectral acceleration, or as it mentioned, response spectrum acceleration at the fundamental period and damping ratio of the building in direction under consideration is the acceleration, response spectrum acceleration. So the earthquake is here. If is a level of the earthquake that is considered in the design code, maybe we can use the, for example, NBCC response spectra for the calculation of this. But if other level of earthquakes are selected, or even for that 10% in 50 years, we can do site-specific investigation and calculate the response spectrum. Therefore, by the way, in previous version of codes, the number of these coefficients were more than the modifications that we are doing. So from version to version, maybe some changes being done in these coefficients. It's not very fixed. But for now, you are focusing on the effect of the earthquake. earthquakes comes to the formula through the SA, response spectrum acceleration. What was the response spectrum? What was the response spectrum acceleration? All our dear colleagues, dear structural engineer experts, they know that it's very nice tool to perform a very difficult dynamic analysis easily. So the response spectrum is showing us the maximum of a response. For example, the maximum of for us is acceleration now is important. The maximum acceleration of different buildings with different periods or 1/t frequencies. Therefore, as you know, the concept of the response spectrum in the code are very nice. When an earthquake happens, the ground shakes, and if we measure the acceleration of the ground, the maximum acceleration in the ground is peak ground acceleration, PGA. So the question is, when the PGA is a specific value, when the ground shakes, what happens to the different buildings? So when we look at the response spectrum, every response spectrum, on the horizontal axis, we should see buildings. Very stiff buildings, small period, to very tall buildings, long. It is around, for example, 10-story building, 2-story building, around 30-story buildings. So we should see buildings. And the response spectrum shows us that the buildings with different periods and usually the same level of damping, 5%, usually is a good measure. If the same earthquake applies to them, what will be their maximum response? So that's the response spectrum. It's not ground motion, for example, spectrum, but it's the response of the building to that ground motion spectrum. Very good, very nice tool. So if we have the period of the building and they provide us either from code or by site-specific study, response spectrum for that level of the earth. So it is decided that we are talking about 2% in 50 years, or 10% to 50 years, or return period of 5,000 years, or return period of 100 years. Whatever is that, give us the responses. So either from code or by doing the site-specific study for that level of the earthquake that is we are concerning, we get the response spectrum. Then for every building with each period, we can have the what is the expected maximum acceleration. Very good. So that's easy. We have it. This part is done. So for this part is really is an input to our study. They will provide us, or a team will provide us. Then there is a philosophical concept here that if a building, we push a building till their collapse, we expect to have a curve like this. We call it pushover curve, or call it capacity curve. It shows the capacity of the building. That a building but the capacity curve depends on the load distribution that you use for pushing. But usually, for example, we use invented triangular distribution, and we increase the load. So building gets little by little damage, and damage means that reduction in stiffness. So stiffness reduces. So when it becomes unstable, the stiffness will be zero. So that's a very important curve. Is the capacity, shows the capacity of the building with respect to base shear and top displacement of that building. Very interesting curve. It shows, for example, the when it decreases to 20% of the maximum strength, that's the location that we can use to calculate the ductility capacity of it. So the capacities are here. The capacities are here. Now that we are doing performance-based analysis, there is a few capacities. Till here is the ductility capacity for I/O. This is the ductility capacity for LS. This is the ductility capacity for the CP. And as I mentioned, when we do the linear analysis, then we use different M's for each of them differently, because these are different capacity levels. So the behavior of the building is this. This is the capacity part. Demand, where is the demand? Demand is dependent on the earthquake. That the building gets to what point, which point in this curve is dependent on the earthquake. If the earthquake is very small, it comes to this. So demand is here, capacity is the whole curve. More stronger earthquake brings it to here, so the capacity is the whole curve, but the demand is here. Demand is much, and the demand is less than the I/O. If earthquake is more damage the building till here, so the demand. So demand is dependent on earthquake. We have different demands for different level of earthquake. One earthquake can bring this building to this here. So demand is more capacity. It collapsed. It even passed the collapse prevention, life safety, everything as it collapsed. So this is capacity, and on different level of capacity, we have acceptance criteria for the different performance levels. So the performance levels are accepted values for the capacity. Demand depends on the earthquake, and then we check and compare the demand with capacity. If the demand is less than capacity, that specific performance level is satisfied. So the building behaves like this in reality. But now for tonight, we are focusing on the linear analysis. Linear analysis means this. If we put that base shear on the software that is models elastically, this gives us this point. Just assume. But if we apply the load to the building non-linearly, it comes to this. So the building in earthquake is here. When we put on the software is here. Note that concept that I was talking is that for us, which one is important? For us, the level of the load is important to be the same between reality and linear estimation, or the level of deformation. We want to say that the level of deformation, this axis is important, not this axis for us. Why? I will explain in a moment. So the C1 and C2 will try to increase the V if needed. To increase the V if needed, that the when we put that increased level of base shear on the building, we get the same displacement that building experience in there. So these two coefficients are there to increase the base shear if needed, that when you, in your elastic model, you put this base shear, you get the same displacement at building your experience in the earth. Why this is important for us, not this one? We increase this, we distort this, we increase this to get this one correct. Why is that? Because our curve is like that. If our curve was, for example, like this, we would do something else. Or if it was a linear, there was no difference. Both this axis and this one was the same for us. But the behavior is this way. So if you want to differentiate between different performance levels, for example, here is 0.1. Here is 0.2. No, here is 0.2. Here is 0.3. If you want to say, if you want to measure that, are we at this point? Are we at this point? Are we at this point? It is difficult to measure it from the vertical axis because they are almost at the same point. When the building, when the element, when the building get welded and the stiffness is near to zero, the force remains constant. So the force is not a good measure of the performance because at this point that damage is less, the force is not that is near the collapse. But the horizontal axis is quite different. The value on the horizontal axis are quite different. So we use deformation measures, displacement measures for performance rather than force measures because our buildings behave this way. Our buildings will lose stiffness. They don't get a stiffness. If it was like some of the mechanical items, if it was increase the stiffness, it was better to put the measures on load rather than the displacement. So for us, it's important that displacement be the same. C1 and C2 are using to increase the value of that comes from the spectrum that comes from earthquake, that when we add increase load to the building, its displacement be a good estimation of reality. But for forces, we distort the forces. We change the forces. Okay. There are different factors. I assume I have the next slide. I discuss that there. The C1 coefficient. What is the C1 coefficient? The C1 coefficient is what it's written there with the wording from the code. Modification factor to relate expected maximum elastic displacement to displacement calculated for linear elastic response. In a way, says that we are doing a elastic analysis. But the reality is nonlinear. Is the maximum displacement in the nonlinear building more than the linear questions in earthquake engineering? From beginning of the earthquake engineering till right now, for every system, for every new system, for every study, they ask that what will be the maximum displacement of this system in there? So estimation of the maximum displacement of the damaged building is a very fundamental question in earthquake engineering. And from long ago, different answers. For example, look at this. When we, this is the lateral displacement of the top of the building in the earthquake. When we did linear elastic analysis, and when we did non-linear. After a while, you can see the building is damaged and move one. So is that much different. Finding that from 50 years ago, the researchers have seen and they call it, for example, displacement principle. It means that for many buildings, statistically, not for a specific earthquake. For a specific earthquake, the maximum displacement of the building for elastic analysis, with inelastic analysis can be different. But if you do lots of time study analysis and in average for many buildings, statistical results happens. Very nice. If you apply the load elastically, you get this distribution. If you reduce the strength, for example, you use a small R value, and building get damaged, but the maximum displacement are almost this. Even more interesting, you reduce the strength of the building, reduce the strength of the building, reduce the strength of the building. Building is so weak now, but the maximum displacement is almost the same. Of course, get damage. Here in elastic, it doesn't get damage. Here you have the plastic deformation, but here you don't have, you are smaller, but the maximum displacement is almost the same. So C1 for many buildings are around 1. For which buildings, this C1 is a dynamic property of system. It depends on the period. For long period, for flexible buildings, for buildings that their period is large, for long period buildings, the elastic stiffness, the same displacement between elastic and inelastic is equality. According to our the buildings that are not statistics. Unfortunately,
Dr. Dr. Moghadam, are you there? Your voice is cutting off.
I don't know if again, it seems
Dr.
okay.
Moghadam?
Yes, sorry, for a few seconds, the internet was, I lost the
Yeah.
internet connection. Yes, but now again,
Right.
fortunately, sorry for that.
Yeah, I think you have to
Okay.
repeat last 3 minutes, I guess. Last 3 minutes, it was, there was some problem.
Okay.
Yeah.
By the way, Mr. Rudra, I will right now. I will go to my WhatsApp. So I will keep my WhatsApp open too. If that happens again, you can text me. Sorry for that.
Yeah, no problem. Yeah, definitely.
Okay. Just a moment. Okay. So the point was that therefore uh, for some buildings that they are flexible buildings. They're
Dr. Moghadam, we lost your connection again. Like we cannot hear you at all right now.
Mr. Rutra, again, do you have my voice?
Yeah, right now I can hear you. Dr. Moghadam, I can hear you now.
You can hear. Okay. Because okay. I wanted to switch to the cell phone, but it seems now again okay.
You can switch to your cell phone. Should
So,
I make you the presenter there?
if that happens, this again we switch to the cell phone
Yeah,
because cell phone
if
is
your network internet connection on your cell phone is consistent, we can shift it. Like I don't have any problem.
okay.
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 Yeah, just let me know
But
next time.
right now it seems okay. If again that happened, we will go to cell phone.
Okay, sounds good.
Yes. Now, it's okay. So, if we this part lost some time, so the C1 factor once calculate the is to calculate the ratio of the maximum displacement of the building to the elastic displacement. Compare these two and for I think again. No, it's okay. Um, so for the buildings with the larger periods, we assume that C1 is around 1, even if the strength of the building changes, becomes smaller, and the building gets lots of damages during the earthquake, the maximum displacement is approximately the same as the elastic buildings. So for the buildings with the larger periods, the maximum displacement of elastic and inelastic buildings are the same. For the buildings that are stiff, their period is small. For them, unfortunately, this principle doesn't apply. And as we reduce their strength, their maximum displacement will increase. So if this building, this stiff building, this shorter building compared to this taller building, if we do the linear analysis, the maximum displacement is some amount. But if we do nonlinear analysis, if the strength is less than the applied load and get damages, the displacement increases than the last. And if you reduce the strength, the amount of maximum displacement increases even more. So in a way, they call again, statistically, the equal energy, the area under this is applied. So the horizontal, so the elastic analysis, the amount of energy on the force deformation curve is this triangle. And if you reduce the strength, this should goes with two more displacement till the same area under force deformation displacement as the original elastic one happens. So the equal displacement is not valid, equal energy is applied. Yeah. Therefore, this C1 wants to model this. If the buildings are shorter, if the buildings are stiffer, and especially when they have less strength, you should, because we said that we want to have the same displacement as the real building. So in our elastic analysis, we should increase the base shear to give us the same displacement as the reality. And one of the source of the change in displacement is for shorter period buildings, especially when their strength is less, their inelastic displacement is more than their elastic. So if you are doing elastic analysis, tonight we are talking about elastic analysis, so you should multiply their base shear by a value to get their real, to get this much here displacement. So we should increase the base shear. So the C1 is showing the effect of the consequence of the a dynamic property of the system, and C1 depends on the period of the building. And usually, the researchers shows that when where is that threshold for the period that a building behaves like as a equal displacement or as a equal energy. What is that threshold is the period of the soil as a general view, the period of the soil. So we look at the building. A building is on a soil. We estimate the period of the soil, and if the period of the building is more than the period of the soil that this building is resting on, then the equal displacement approach is governed. I just show something here. Sorry. And usually the period of the soil is this one. For example, different SA, SB, SD, the period of soil is this for each group. So if for the buildings that resting on SA soil and their period is more than this value, their equivalent displacement principle applies. Just a general, having a general view that what is the idea is good enough, because the details from each code to another code, for each one code from one version to another, it changes a little bit. But generally, all of them has a coefficient like this. The other coefficient, the C2 coefficients, I checked the previous one was C2. No. Sorry for that. Again, should we increase the elastic base shear to have the same displacement, to result in the same displacement for building as the reality due to the other factors? Yes, one factor was that period of the building is important, and the inelastic maximum displacement of the buildings are different from the elastic one based on their period. But there are other aspects too. One very important for existing building is this, the shape of the hysteresis curves. The shape of the hysteresis curve is very important. And usually when a new seismic system is being designed or invented, the inventor tries to show that this systems has a very stable hysteresis loops. He wants to show that the seismic system should get damaged in specific points, for example, in moment-resisting frames in the beams like this. And those points that get damaged, we call them deformation control parameters, fuses, plastic hinges. We expect that those can dissipate lots of energy. And energy is in the area inside the force deformation curve to have a stable. But many times after one or two cycles of the earthquake, this stability of and this nice fat hysteresis loop will change to something very very narrow, and it seems like it's pinched. And the area that we expect that reduces and absorb the energy, earthquake energy is very reduces. So naturally, we can agree that if the area of the plastic changes that absorb energy reduces, for an earthquake that impose a specific level of energy, this one with this pinched curve, it should move more, get more displacement to have the same level of energy dissipated as this original. This one, this fat one, with a small displacement, dissipate lots of energy. This one should get more deformation to dissipate the same level of energy. And therefore, this C2 factor is here to show that if the hysteresis curves are not as good as they should be, we expect this building will have more displacement if we do non-linear analysis. So in the linear analysis, we should increase the base shear to get the same displacement as the reality. The reason for this is the detail. If the hysteresis curve is good or bad, is depend on its detail. If there is a pinching, what is pinching? Pinching is like this. Pinching is that we have some distances in the curve that they are almost horizontal, or their slope is not anyway, is not that much, almost zero or near to zero. So that's what that means. It means that you have horizontal value without vertical value. Then it is horizontal. You have deformation without force. So these parts, it will moves without need of imposing forces and get extra deformation. And that happens for many things. For example, when a beam has in bending get lots of cracks. So when it gets lots of cracks, when we want to impose a bending moment to that, first the cracks should enclose, then the stiffness increases. So there is a distance that it moves without that much force. So it doesn't dissipate energy. Or for example, a building that their braces are buckled. So we have a buckled brace right now here. So now that loads goes from one side to another, first that buckled brace should strengthen. When it becomes straight, then it absorbs. Or if there is a slip, if for example the lap splice in the between reinforcements are not enough and it slip. It slip means you have deformation without forces. So anyhow, all these bad events are due to the detailing. And this is especially true for existing buildings, because new buildings, if you look at the coefficient formula for the new building, in some codes, they also put this for the new building to do performance-based design for new buildings. There you don't have C2, because for the new building, you expect that detailing will go. So you don't expect that in the cycles of the needed number of cycles during earthquake, this pinching happens. It should be very stable, good detailing, everything good, lateral reinforcement, all the confinement, everything is well designed and implemented, so you don't expect this kind of behavior. But in the existing buildings, this C2 is very. Therefore, what was the use of the C1 and C2? We wanted to increase the base shear, elastic base shear, that when we apply this in our linear software to the building, the building gets the same displacement, maximum displacement as the real buildings. But sometimes there are some factors that can decrease the displacement, Then usually the modal mass of the higher modes of the buildings are important, that can reduce the displacement too. So sometimes we can use 0.9, 0.8, and 10%, maximum 20%. You say maximum 20%. We let that decrease the base shear and the displacement to the higher mode. Because when the higher modes are important, so you can see some loads is not like first mode, that all the load are one side makes this larger displacement for the building. Here, some of the loads are in one direction, some are in another direction, so it reduces the displacement, the top displacement of the building, if the higher modes are important. Usually, they provide tables for different systems, and based on the number of floors, number of stories of those buildings, they give some estimation recommendation for the value of C. Therefore, all these coefficients are used that to modify the base shear, elastic base shear, that we get the better estimation of displacement. Later, we see that when we want to have a better estimation of force, we will divide those by C1, C2. When we want to have a good estimation of displacement, this C1, C2, and Cm should be there to give a better estimation of displacement, because we are doing linear elastic analysis. We don't see that the maximum inelastic displacement is more than elastic displacement. We can see that due to the pinching behavior in hysteresis curve, due to the inadequate detailing, the amount of energy that is dissipated is less, and the building get more displacement in this badly detailed building. So with this, now we have a good demand estimation. Now we should do our estimation with demands. So the next step now is the distribution of this force. Is the linear analysis. For linear analysis, the superposition is there, so we can apply first the lateral load, then the gravity load cases, and combine them together. Very nice, very beautiful mathematics for the elastic analysis superposition. So you saw software analyzes the buildings, and then you introduce load combination, and due to the superposition, software combine the results. But of course, in nonlinear analysis, that's not true. If you do a pushover, for example, nonlinear static analysis, if the the gravity load is there, you push, changes happen at a specific location. If the gravity load is not there and you push, the distribution of hinges completely different. And then if you combine the result of the gravity load, for example, with this one, the results won't be similar to the other one. The superposition is not valid in nonlinear analysis. But for the linear analysis, very nice. You have the estimation of the base shear. We modified the base shear that give us the same maximum displacement as real building. Then we distribute them similar, almost similar to the one approaches that we use for the new building. Just distribute that, and also we can use the load combinations, gravity loads there, and because it's linear, they can be done separately. Not there is no need to put all the loads at the same time. And again, you can see that from code to code and different version of code. For example, in previous version, we didn't have the snow load in the gravity load combinations, but now we have snow in some of the codes. We have a snow load. Generally, load combinations, both for gravity and gravity plus earthquake, is the number of load combinations is less for existing buildings. Because existing buildings, at least there is less, we have more information about the use of this existing building. This existing building is, for example, a school. For this room, you have even the distribution of the all the equipment there. So because our estimation of the loads are more accurate, usually there is no need to do the overestimated estimation that usually we do for the new buildings, because we are not sure that what happens to loading of this new building. Is the distribution of dead load, live load will be exactly as we expect, as we design or not. But here in the existing building, you can check and see what is the distribution of dead load, live load. So the number of load combinations are not that much. Usually a larger gravity load, and because sometimes if you increase the gravity load, then it's not safe for designing some of the elements that, for example, the uplift will happen to them. So if you increase their gravity load, the uplift will reduce. So you are not doing a safe design by increasing that. So usually codes have a smaller value of the gravity load proposed for the anchors, elements that due to uplift, for example, if increasing the lateral load, vertical load will reduce their design values. It's not good. So in fact, we have more or less two main gravity combinations. Then, when we have our building for linear analysis, now we can calculate the demands. But unfortunately, because reality is nonlinear behavior, our methodology for now is linear, so there is some modification are needed in the results. And right now we want to talk about those needed modifications. Therefore, we put the different, as a different load combination, we put the every one of the gravity loads as a vertical load, also the lateral load, the earthquake load, and get the responses for the gravity load and for the earthquake. So QG is action, any response in this beam, in this column, in this shear wall, different responses that they are axial, bending, torsion, action caused by gravity loads, action caused by, so the Q is the consequence of these loads. When the loads apply, when we use Q, we mean the different responses due to that load. Therefore, what will be acceptance criteria for deformation control actions? And what modifications are needed? What modifications are needed for the deformation control actions? What was the deformation control actions? So we shouldn't mix up, very easy. We found the loading, as usual, elastic analysis. We impose the loading on the building. Now we are looking at the responses. Some of the responses are dangerous ones, force control responses. We want to design them based on strength. We don't try to get help from the ductility. So just a strength design for them. They are force control. Somewhat are the ones that they have ductility, good ductility, and those are the responses that we selected to get damaged. They are deformation control. So for the demand on this deformation control elements comes from the application of the gravity load plus earthquakes. So, for example, bending in this beam, now you have the maximum value based on the applying the gravity and earthquakes. And these are action caused by gravity, action caused by the seismic. Now, what is the problem? What adjustment is needed here? What is our problem with the deformation control parameters in linear analysis? Our problem with deformation control parameters in linear analysis is linear analysis doesn't show the damaging, but in reality, the deformation control actions may get damaged, and we need to measure the level of their damage, because the performance level is based on the level of damage. But the classic analysis doesn't show us the damages. So what we should do, how we solve it, with using these M factors. So if we find out the demand in the displacement in a deformation control parameter, the demand in deformation control parameter is more than capacity of expected, or expected capacity of that element, expected because it's deformation control. Capacity of that, still we don't say that the building is failed, the building is collapsed. But we look at the values of M that somehow give us a sense that how much damage is accepted for this element. So, and this M value naturally should depend on the properties of the element, also for the performance level that is selected. And then there is a knowledge factor I will explain later. Therefore, one of the most important contribution of this new series of the in this decade, I mean this last 10 years or even more of the existing building code is the tables like this. Such a nice table. Such an important table. Just you structural engineers can look at this table and enjoy. Really is enjoyable. Even in the Sundays around 10 p.m. Because for example, this table is for the for acceptance criteria for linear provision for reinforced concrete beams. So this is an existing building. These existing buildings, different beams, different situation, different conditions for the different beams, but with a few parameters of each beam, you will decide about its fate. For example, the level of ductility, the level of the transfer reinforcement, and the level of the shear. You say that the M value for LS is 3 or 6 or 2 or 10 or 1.25. So here we have the M values. It's like R factor. What R factor? Because we had a Class C building, everything is good in that. It is supervised by you, dear structural engineers. Everything that was not good, you said you should demolish that, make it according to code. All the details are implemented in design, in construction, so the whole building has a R factor. But we are talking about an existing building. One element is good, one element is bad. One element is 1.25, one element is 10. One element, 125 times their capacity is allowed to have force in elastic analysis, this much damage, but one is 10 times. And that's the beauty of this, that the tables, that element by element. It's time consuming for us, but the most important, the costly thing is that you want to, for an existing building, go and do retrofitting. Disturb everything, it's very costly, it's very difficult. So it's no problem, element by element we check. Otherwise, we should use 1.25 for all of the building. What is the R value of this 125? But it's not, so for some as 10, for some as 4, for some as 6, for the same. So depend on the element. Now is the reinforced concrete beam. For the bracing, for the shear walls, for all the elements, this kind of tables are there that next Saturday we will also discuss some of them. But this is very important contribution of these codes to the systematic retrofit. Based on a couple, for example, 3 characteristics of each beam for each level of the performance, life safety, collapse prevention, IO, we have that in elastic analysis, very simple, the things that we are used to. In this in elastic analysis, the demand right now in this beam, the demand, the bending moment is how much? It's 3 times the capacity of expected capacity of this. But if it's 3 times, less than 3 times, is didn't pass the CP limits. It didn't pass the CP. For this one, because it's very good beam, till 7 times, we let it to the demand be 7 times than the capacity, and we say it didn't pass the collapse prevention. This one 6 times for life safety, but this beam is not that good. The ductility of this beam is less. The transfer reinforcement are not conforming and are not good according to the requirement that we want. And the shear, in the reinforced concrete, we hate shear. In steel structure, we hate slenderness and buckling. So if the shear is more, it will reduce the M values. So the M values, which shows the ductility of the element, is like the R factor, is depend on the condition of the element. And for one element with a specific condition, depend on the performance level that we are studying. Of course, if you study that for IO, we limit less damage in that. We accept less damage in that. But for LS, more damage acceptable. For CP, more damage. So M factor for a specific, and all the tables, everything that we discuss is for deformation control. For force control, we don't have anything to do. Force control shouldn't pass the strength. Easy. And the strength is calculated with lower bound value of the material characteristic. And that's it. Everything, all the discussion, all the new thing, all the exciting things are about the deformation control, about the fuses, about the location that can get damaged. So in these tables, we can see that we have a very good summary of years and years of the experimental work and results and experience of knowledgeable engineers that put together and reach to these values and make our life so simple that for whatever situation that are the elements in the building have, we have the acceptance criteria. Acceptance criteria for that deformation control parameters. Depend on the condition of the elements and depend on the selected performance level. So, nicely and very complete. For example, for different conditions, if the beam control by flexure, it was shear and different conditions and different situation, the values are shown in the tables. So, and these values, these M values are calculated, as I said, based on mainly experimental investigation and results of past studies that cyclic test on the materials and under different, every one of those conditions. If you use, for example, condition 1, how much ductility is there? If you use condition 2, makes more, the behavior becomes more brittle, so we should use less M values. All this, and the way that if you want to calculate the M values. It is explained in this course if you want to do. If you have designed a specific, for example, element and want to find the M value for that based on the results of your experiment, the way that you extract the M from the experiments are explained. The other thing for the deformation control, so for force control, but mainly for deformation control, is the value of the kappa, the knowledge factor. Are many places in the world, in almost all countries, the most difficult job for the systematic retrofitting is to reach to the model, to understand the building, to be sure that the thing that you are modeling is not that far from the reality. How many reinforcements are there? How's the lattice splices? How's the dimension of the beams? How's the quality of the material? So in these codes, they have a systematic, nice approaches, flexible approaches that give you some level of selection, some level of flexibility. They don't say that you should do this many tests here, because sometimes they don't let you to do this many tests. So if you, instead of, for example, testing, instead of doing this level of testing or this level of testing, you do for this level of performance and this level of analysis. For example, you go with test, then you have a smaller knowledge factor. Therefore, the knowledge factor is usually for the if each performance level, each analysis method that are we using, based on the level of the information, especially number of tests that you are doing, is being provided. So sometimes you say, it seems this building is, the results is obvious. There is no need to damage that too many places to test. So you go with the less number of tests, use less number of, knowledge factor. But sometimes you see that if you use less knowledge factor, it's almost at the boundary that you accept the building or say that is vulnerable. So it's better to do more tests and use the knowledge factor equal to 1. Because how the knowledge factor is applies, the knowledge factor is applied to the properties of the existing elements. For the new elements, for example, if you are using some new elements to retrofit the building, those new elements, you don't need to reduce the capacities, because they are new elements, and and you can supervise the way that they should be designed and applied. But for the everything is for the, for example, here in this table, for the linear analysis, which is our case, for deformation control capacities, for force control capacities, for existing material strength. For existing material strength, for the deformation control, we say we use expected mean values. For the force control, we say lower bound values, which is the mean minus 1. But for the, then there is this couple knowledge factor, it just will apply to the capacities of the existing element. Capacity of the deformation control, capacity of the force control, capacity of force control is lower bound, capacity of the deformation control are expected, the kappa is multiplied by that. But for new elements, you don't apply the kappa. The same for our talk on Tuesday for the nonlinear procedures. Again, the kappa will apply to existing components for the deformation limit of the existing component, or for the force control ones to the strength of the force control, lower level capacity of the force control element. That's a very good scenario that give flexibility because if they just give one way, you should do and do this many tests. Many times that is not possible. They don't let you to damage the building, for example. So you should have some level of flexibility, and using this knowledge factor is a good plan that they did in the codes for existing buildings. So what was the problem with the deformation control and how it's solved in the elastic linear analysis? What was the problem with the deformation control actions? The problem was the linear analysis cannot implement the damage in the deformation control elements in the model because it's linear. So how it's solved? By introducing M factors. Okay, so if the for the deformation control parameters, if the demand was more than capacity, we look at how much is this DCR, how much is this demand to capacity ratio. If it's less than the M value assigned based on the condition and the performance level of the element, which is okay. So, yes, we can see the amount of damage in this element, but using the M factor, we say till M times capacity is more than demand. It's okay. Now, what is the problem with force control action? What adjustment should we do for the force control actions in linear analysis? Two modifications should be done. Two modifications. One is, two modifications should be. One modification is that we increase the base shear by C1, C2, why? To have the maximum displacement as reality. But now we don't want, we don't concern about displacement. We are concerning about forces. This is a force control element. So for the force control elements, we increase the base shear by C1, C2. Now we decrease the by C1, C2. So we increase the base shear, everything is linear, so even the force control parameters increase by C1 multiplied by C2. Now, when we want to check the force control parameters, for example, shear in this speed, axial load in this speed, torsion in this speed, we divide that by C1, C2. We say that the amount of lateral load that we impose to the building is too much. We impose that to have the building the same displacement and reality, but to check the deformation control parameters. But for force control parameters, we want to a good estimation of force distribution. There is no need to C1, C2 for the force estimation. And what is the J? There is another point too. Another point is that there are estimation of the force controls by linear analysis is not true. Even if we divide by C1, there is very important issue that linear analysis can't see. And that's the nonlinear behavior at the deformation control parameters. In seismic design, why we put the deformation control parameters, why we put fuses, because they get damaged and they don't transmit load to the brittle elements. But in the linear analysis, can't see. If we do nonlinear analysis, we see that during analysis, this beam get damaged, the plastic cable, and if we have a beam that both side of that, both end of that is damaged, so one end, the maximum moment is M sub P, for example, plastic moment. The other part is M sub P. So the maximum shear in this beam, if we use equilibrium, will be 2 times M divided by length of beam, which is A. So never we can impose more shear to this beam than 2 times MP divided by A. But in our analysis, because it's linear, you multiply the force by 2, shear goes 2 times, 3 times, 4 times. It doesn't show the behavior of hinges, the behavior of fuses. These fuses are there to control the load transmission to the force control elements. But it's linear, can't show that. Therefore, we need to use a factor to reduce the value for force control actions due to the damage of the deformation. So, for making a better estimation from the force control parameters, we need to make 2 adjustments. Chi, we don't need right now, but is a factor, again, in our methodology that if the force control is very important, is not that important, if there is, what is the consequence, it can be different values. But for us, this part is very important. Therefore, for the for the deformation control parameters in the linear analysis, we use the M factors, but for force control, we don't use M factors because we can't accept their demand be more than their capacity, but at least calculate their demand in a better way, not this much conservatism, because the deformation control element, parameters, when they get damaged, they will control the load. But we can see the elastic. By C1 and C2, we increase that to get a good estimation of deformation, not forces, so not reduced by that. Therefore, some parts of code are mentioned here that how to calculate this J, how divide by C1, C2 is clear, but for J, there are few ways of the estimating that. First is to look at the damage in the those deformation control elements. If they get more damage, then they will control better the amount of the load in the force control. But if the fuses are not damaged yet, so the value that we have in the force control parameter is correct because the fuses are not damaged. Or simpler way is depend on the region. For example, it says that assume 2 for high level of seismicity, 1.5 moderate level. Anyhow, all of these are approximate. None of them are accurate. But it shows that when we use linear analysis, we have some problem for the force control and displacement control adjustments, and these are the approaches that we do there. And therefore, for controlling the deformation control demands, the force control demands, we don't have M. Just we do a better estimation of them by dividing by C1, C2J, and then the lower bound capacity of the force control parameter should be not less than demand. And formula to calculate the shear, for example, capacity of beam, torsional capacity of this beam, axial capacity of this beam is the same formula that we have in code. But for material property in that formula, we put lower bound values because we are talking about force control actions. These are brittle actions, so we do some level of conservatism in the calculation of the capacities. Therefore, the linear analysis is not bad. It needs some adjustment because, okay, we are doing, instead of reality, non-linear analysis, we're just doing linear analysis. Now, naturally needs some adjustment, but it's not generally that bad. So what we do, we model SAB, whatever software that is easier for us, the same as usual. Put the gravity load, calculate the from the response spectrum period of the building, we get SAA times the weight of the building, and then modify that the base shear to have the same displacement at the real building, so multiply by C1, C2, and Cn, and distribute the load here, and look at the elements. For example, this beam. For example, this beam. In this beam, there is axial force. It's not axial force if it's a rigid diaphragm, but assume there is some axial force here. There is a shear in this beam. There is moment in this beam. There is torsion in this beam. And just this one is the deformation control. In reality, if it comes to it passes the strength, we don't say that it's collapsed. We say how much it passed. Is it this much of damage? Is it acceptable for that performance level or not? This shows damage in linear analysis, that the demand is more than the capacity. The demand is more than the strength. In reality, it becomes nonlinear, and for the level of the ductility that it has, we calculated based on this the M factor. So linear analysis can follow the nonlinear behavior of the element, but this increase can be a good measure of the or estimation of the damage. So we use linear analysis. We can't really calculate the damage, which is this, but we use DCR, the demand divided by this capacity, so it shows how much damage. Only in deformation control parameters we accept some level of damage if it's not passing the limits, that M factors. But for others, easy. For others, for force control, are easy. They shouldn't reach to the strength. Again, force-based checking, strength-based checking. These are very easy. So, and how we calculate their strength, the ordinary formula, but putting the lower bound material characteristics in the formula. So we check the demand, the red one are demand. The demands we adjusted, they divided by C1, C2, and J for this. And they are fortunately all satisfy the requirement. All of them, for them, their QA, QCL capacity, lower bound capacity of them is less than the lower bound capacity is this. The lower bound capacity of them is more than demand. QUF, QU, force control, the demand in the force control. Therefore, when we look at the procedure for the evaluation of the building, for systematic evaluation with linear analysis, we have to estimate the demands. So give us the response spectrum for the earthquake that you want, the earthquake that with return period that you want. Based on response spectrum and the weight of the building, we calculate the base shear. We adjust the base shear to give us the same displacement and reality with C1, C2 times Cm. Then we look at the responses. We do some adjustment in the responses, full adjustment for the force control responses, and check with the lower bound. For the deformation control parameters, we don't adjust the demand, but look at that how much the demand is more than capacity. And based on the condition of the element and the performance level, the accepted damage is a coefficient times this, an M factor times this. So there is a test coming, and so it's good to summarize the things that we had. Will be most probably will be good for test at least. So for each performance objective, what are main parts of the performance objective? A performance objective that we start our evaluation, systematic evaluation, start by assigning or selecting a performance objective consists of a earthquake hazard level and a structural building performance level, target building. We have R factor in EMBC, and we have M factor in systematic evaluation. What is their difference? R factor is the same for all building. We divided the whole demand in the building by R factor, but N factor is dependent by element condition of each element and each performance level. So is element level. We have a C1 factor. The modification value to relate maximum displacement to this calculate for linear losses. This factor depends on what? What properties of system? What properties system? Is mainly to the period of longer period buildings, equal displacement approach C1 equal to 1. Lower period buildings, C1 is more than. Their inelastic displacement is more than elastic displacement. Why the linear analysis method is not capable of determining the deformation control parameters? Because the deformation control parameters get damaged. They behave like this. The stiffness changes, they get damaged. But with the linear analysis, the stiffness matrix is not changing, no damage. With this eyeglass, you can't see any damage. It just shows that you increase the load, the displacement increases with the same. So the problem with deformation control parameters is that in reality they get damaged, but in linear analysis they can't show those damages. Then there is another factor, C2, which is two-line definition. The modification factor to represent the effect of pinched hysteresis shape as strength deterioration on maximum displacement. Because it becomes like that instead of what we like, that are detailing. The factor C2 is mainly dependent on detailing. We want with good detailing to have a stable hysteresis behavior. But unfortunately, many of our existing buildings, they don't have all the requirements of the detailings, all the things that is mentioned and listed in the section on ductility in design codes. Therefore, C2 is detailed. If a force control action does not satisfy acceptance criteria, what is the performance level of the building? Nothing, gone, dead. Performance for force control actions, one force control action in the building, in one element, one force control action is not past the lower bound strength, we say that the building is gone. No performance level is IOLSCP no. First, all the force control actions should satisfy. When all force control actions satisfy their lower bound strength, then we go to deformation control parameters, see how much damage they get, and what is the M value. So it's 3 times, and but for LS, the M value is 2 times, so it passed the LS. But for deformation force control is the red line. If we pass the force control, building is gone. Why the base shear increased by factors C1 and C2? Because we want our simplified, simple, elastic analysis give the same displacement as the building in real behavior, non-linear behavior. So if it's not, we should increase the load base shear to give the same estimation. Where is earthquake in the base shear formula for linear analysis? The earthquake hazard level is represented by C1, C2, no, CM, no, W, no, SA. Earthquake is in the response spectrum. The response spectrum that they give us is for a specific level of the earthquake. If there are another level, if the return period is more, gives us a larger values. So SA, which is the response spectrum. The linear analysis method is not capable of determining the force control parameters. Why? Yes, it has two deficiencies. For force control parameters has two deficiencies. One, because we increase the base shear to have the correct displacement. So by doing that, by increasing the base shear, we increase all the force control parameters too. So their value is not correct. We should correct. And another important thing is that linear analysis cannot show the difference in the distribution of load after damage in the deformation control parameters. Deformation control parameters will damage, and when they damage, the stiffness matrix changes, the load distribution changes. But the elastic analysis, linear analysis cannot show that. For a linear analysis, when dynamic methods should be used instead of static? When the strength irregularity happens, strength irregularities, if it's too much, it's better to do non-linear. Strength, non-linear. But if the mass or stiffness irregularity has happened in the building, the dynamic results give much better distribution of the load compared to the static. So what is expected from two-night review is the shortcoming of linear analysis. Base shear formula would be somehow familiar for us. We should know that for force control parameters, we use a load combination that force control be divided by C1, C2J. But for deformation control, we use another load combination, which is gravity load plus earthquake load. We don't divide by C1, C2J, which is here, this one. And we should generally be able to apply the linear procedure to assess limits. So now we are at the point that we can go through the question and answers, which we should first. Okay, question and answer. And I see no question. Oh, yes, there are some.
Dr. Moghadam?
Yes, please, dear Mr.
Do you see the question answer or?
No, I can see, yes. The first one is, can you suggest?
Yeah, that one. That one only.
Yes, because the first one that I have is, can you suggest a textbook that explains the performance-based analysis easily?
Yes.
Okay, okay. There are many good books, but maybe a couple handbooks. The handbook for with I think Buzornia and Buzornia and Bertero, uh, one of the earlier ones. But after that, again, we have many good references. If you search by the same name, seismic performance-based design, you can find very good books and handbooks, including that handbook, famous handbook by Bertero and Buzorgi. According to my understanding, conducting evaluation of different performance level requires different ground motion parameters. But in BMBC, we have only a single set of ground motion parameter for performance level, CP most probably. If we want to evaluate a structure for other performance level like LS, IO, we don't have enough information about the respective ground motion parameter. In that case, how we can conduct our systematic evaluation using, for example, capacity spectrum method for different performance levels. Uh, uh, First of all, the way very professionally our colleague mentioned, because in many of the codes, they assign the earthquake hazard with the relative performance level. For example, as you can see in the question by our dear colleague, for example, he mentioned IO 20% in 50 years. And it is true in quotes, but in general, the main objective of the performance base was to separate them. It's not always they act attached together. But IO is always with 20% earthquake in 50 years. It's not relevant to your question, the thing that I'm saying. But because you very nicely pointed out, I wanted to first say that yes, in the codes usually they give some recommendation how to which pair you use, but the general performance-based approach is they are completely independent. You can select, and the good point is that we should be able that whatever performance level is selected for whatever earthquake level, we should be able to check it. So it's not that always they say check CP for 2% in 50 years. Maybe they said check CP for example, 1% in 50 years. The selection from the earthquake with the performance in general can be whatever they want. It's not fixed. But your main question is not that. Your main question is that we need the different the response spectra for different earthquakes. And that's true. In most of the important projects, they do the site-specific response spectrum. They derive and do the hazard analysis. Therefore, we can do that. Also, there are some recommendation that to derive different response spectrum for different return period from each other, which is, of course, very approximate. But for example, many times you use the coefficient 1.5. You see in the works that they use coefficient 1.5 to change the response spectrum from 475 years to 2475 years, from the 10% in 50 years to 2% in 50 years by a coefficient of 1.5. So is depend on the project. If the peer review team, the advisory team, let you can use some modification factors from one level to another. Or they may let you to use the different studies that have been done and are being done. For example, in case of DACA. So you may have studies under this URP project, for example. Studies have been done that for different level of hazard, I think is almost done as far as I know, that they can suggest you the different. But in the worst case scenario, they do the teams or you yourself can do the hazard analysis for the specific site. But the question is valid and how much time and money we should want to invest. There are different ways to, with different level of the accuracy that we can do in the real projects. Our dear colleagues mentioned, can you please show us the formula of SA in this shear calculation for existing building? It would be better for our understanding we kindly put any example in your lecture, which is very good. In fact, most probably my last presentation on Saturday, I will explain that how a small area of the evaluation and retrofitting of the existing buildings is covered in this course. It's just for showing some concepts and what are other areas. Let aside the examples, which is very good, but it takes time that go through examples. Therefore, you are right. That's a deficiency of the lecture, that there is no good examples then, but there is not a tomorrow we have again this in the day after tomorrow, on Tuesday, for the nonlinear approach. Again, here we calculate the base shear. There we calculate the target displacement as a measure of the earthquake, as an effect of the earthquake. Here, earthquake, what is the earthquake? It makes a base shear. There, what is the earthquake? Make a target displacement. In there, the calculation of target displacement, again, we use the SA calculation and the spectrum. So I will try to cover your question on Tuesday in that part. But for the examples, I think is not really possible. And then thank you very much. Some of our during that problems that I make with my internet for you, they give me feedbacks. We know we need to calculate Vy elastic to find out M factor of the M factor of column in tier 2. But without nonlinear analysis, can we predict Vy of buildings? Again, with the estimation can be done, because uh, you can assume, you can, for example, for a steel building, uh, because for different level, you can give as an output the stress ratios. So it gives you a sense that at what level of loading the elements stress ratio becoming near one, for example. So give you a general estimation that is not bad, but because usually with a couple a small nonlinearity in the element is not really that yielding point for the buildings. Yeah, because there should be a few of the nonlinear, big nonlinearity happens, then the general stiffness reduces towards zero, then we can calculate that. Again, if you let me tomorrow, the day after tomorrow, in calculation of target displacement, there we making the capacity curve bilinear to calculate the Vy. I will try to also give some thought here about a very good question. Our dear colleague asked, can you add some retrofit? Okay. That was one of the shortcomings that I wanted to explain on Saturday, that usually in these codes and these courses, you see that the topic, for example, the topic of the code or the guideline is seismic retrofitting of the buildings. But there is no detailing of retrofitting. You see that you need some, for example, innovative approaches. We explain them, but it seems that they are not as much as needed. They didn't attention as much as needed to the retrofitting details, and that's because that's because really the main contribution of the systematic evaluation is not the retrofitting techniques. Retrofitting techniques and innovative retrofitting techniques are very important, but it's not really very the main topic. The main topic is modeling for the evaluation and the retrofitting. And what the most innovative things that happens to the retrofitting these years is this modeling. Because in the modeling, you can incorporate whatever deficiencies in the building and do the evaluation. But applying, for example, base isolation, applying shear walls, applying these systems, then to the building, when you have the modeling and comparing the results is not a big deal. It's very straightforward. It's mainly use of software than the concepts. It's not anything new in that. Just how to when you have the modeling, how to apply that. So because of that, you don't see that much attention. But in application, of course you need. But I mean, it's not the priority. So is one thing that really I didn't put in my part two, but on Saturday I give you when I want to say that which parts are not covered, I will try to give some general approaches, because there are some general approaches. For example, they say there are 7 specific deficiency buildings, and there are 5 approaches to remedy them, and how they check this, how they, based on for every different systems, how they check these 7 deficiency with those 5 remedies and find the best retrofitting and then doing cost calculation. At least I will try to give you a couple good references. I remember one, but because the number I'm not completely sure, I will try to give you at that. And all are free to download. This one is about the detail, about the retrofitting the techniques for different deficient buildings. I think it's FEMA 574, but I'm not sure of the number. I will check and will tell you. And another thing that our dear colleague very well emphasized is even the common mistakes in retrofitting calculations that and in the implementations. What are the common mistakes? And along with his questions, what are the what are the subjects that you can enhance in your modeling? Because to reduce the cost, we have at least 3 general approaches in retrofitting. One is that one of them is to increase the depth of modeling. For example, you model the soil, you model the connections, you increase the level of modeling. One is to increase the number of the, for example, the retrofitting schemes that you can imagine. So find the most cost effective. And of course, the last one is using different analytical analysis for them. Anyhow, the table 1013. How can we get the value of V? Which load combinations should be used to get the value of V? Very well. For example, the sample that I put there was for the reinforced concrete beams, and our dear colleague noticed that there a measure of the ductility there, which is rho minus rho prime, the tensile reinforcement and compressive reinforcement ratio, that is a measure of ductility. Then there was a measure of the last was of the measure of the shear, that was the shear demand to capacity. And his question is that how we calculate the shear demand. Usually, if you see, there are colleagues do different things. Of course, the most logical one is that for every load combinations, you use the same load combination to calculate the properties of the modeling. But because it's become sometimes time consuming, at the beginning at least you do the worst case scenario based on the load combinations, the one that gives the most value for V, and use that for others. Then you look at the results. If you see that with a small change in the results, you may get better results, then it's worth it to go and for each load combination by load combination, look at the values. Then our dear colleague asked the same table for IML transverse enforcement should be. Oh, okay. Thank you. Notice that there is a error in the tables. In fact, the tables that I took copy paste was from AC41, and as our colleague mentioned, some of them they have errors, but they provided some supplements for the to correct those errors, but I just copy from the original text. Then I think he didn't ask about the errors. He said should be N or not, should be N or NC. No. But your question was not about the errors. Because, I thought you said that one of we changed the no. Here not the NC is used for not conforming. So if the existing detailing conforming to near to the what code wants, we say this is conforming. If it's not conforming. So is conforming or not conforming. Then is there any problem viewing screens? Oh, sorry, lots of problem. You are right. Please, yes. Thank you for feedbacks during presentation. If we get CP performance level from pushover analysis, so we did pushover analysis, which is the subject of our Tuesday talk. Is it okay for existing hospital building without retrofit to get CP? As I was discussing with one of our dear colleagues about the dependency between performance level and performance hazard levels. So it is important that this CP performance level is with respect or corresponding to what level of earthquake. If it is earthquake, a small earthquake with a short return period, they cause CP, we can make one decision. If a very huge earthquake with a long return period, they cause CP, is another story. So it's not the performance level itself. When you decide the hazard level, then becomes a decision. So if just we look at the capacity curve and shows that this capacity curve goes elastic, then it becomes inelastic, then you should also look at that that collapse happens at target displacement, which is corresponding to what level of earthquake. If it's this level of earthquake that caused collapse is large enough, it is okay. Oh, sorry. Again, many feedbacks from our dear colleagues. Then our dear colleague said, when we have our BMBC, why we use ASCD? But for the existing buildings, one of the most well-established codes is AC47. Of course, most of countries, they have developed their own codes. But if you look at the codes that are available, European codes, Japanese code, Turkish, Iranian, some African countries, they have retrofitting codes. But generally, Indians codes for retrofitting an evaluation. Usually, they are not that far from the AC approach. So because they kept good order of the changing their versions, so it is good. But of course, every country like Bangladesh should develop their own code for retrofitting too. Because just there are enough many information in BMBC, but again, even there are information about the existing buildings in BMBC, but not all the information that is needed for the systematic retrofitting is included in the building in the codes for the new buildings. So we need for now, especially for acceptance criteria. Yes, sorry. It seems that it was not very good to the audience. Many of part of the lecture and caused problem for our dear colleagues and their time. The linear analysis method is not capable of determining the force control parameters. Can you explain that one more time? The linear analysis method is not capable of determining the force, but yes, the parameters. Can you explain that one? Yes, of course. There was two aspects when we want to check the force control parameters by linear elastic methods. The first part was the way that we calculated the base shear, because we increase the base shear, and when you increase the base shear, we had a good intention. We wanted to have the same displacement as the building experience in the earthquake. But this increases the force control parameters too. So we should reduce that. That was one modification that is needed, that you increase the base shear to do your calculation for the deformation control parameters correctly, but you increase the everything because its superposition applies and all the parameters multiplied by the same factor. Well, so we should reduce the by C1, C2 to remove this increase. The other one, which is more important, is when the building get damages, the distribution changes. For example, assume in a connection, if the stiffness of beam, the stiffness of column, for example, is twice of the stiffness of beam, then when the moment distribute at this connection, two times goes to the column, one part goes to the beam. But when the column damages, its stiffness decreases. From now on, the half of the load, for example, goes to the beam, half goes to the column. So the load distribution changes. But the elastic analysis doesn't consider the change in stiffness, doesn't see these changes. Therefore, the value for the forces are not correct. Because of that, we try to also consider that very, very approximately. And with the J factor, so if we notice, if we look at that value for J, is at the almost level of 2. So with that level, the building is not that much experience nonlinearity, and the results of linear is not that much far from the nonlinear part. And if the building gets more damages and the DCR increases, then we can't use linear analysis. So this approximation that is there for, with J is good enough. And if the building is experiencing more damages, you can't use the elastic analysis. So for the level that you can use, this approximation is not bad. Our dear colleague asked, does the linear analysis include the cyclic stiffness degradation effect, or only indicating C2 is nonlinear, as we can consider that? In fact, the hysteresis curves in the systematic evaluation codes, like AC41, they included the cyclic behavior. So it's not like you derive those modeling parameters from monotonic loading of the element. It's based on cyclic, so the effect of the on deterioration on elements are there. And can you please take necessary steps to upload the recording immediately at the end of the webinar? I assume our dear colleagues taking care of the presentation and recordings. But, okay. Dear Mr. Rudra, already answered. Thank you very much. Can we execute performance-based design or resilience-based design for a new building? It depends on the authorities, because the tools are available. So the tools are available, but maybe because there are some, these concepts are advanced concepts. That's true, but sometimes the softwares, the approaches, the assumptions that we will take in them is very important, and we shouldn't really go quickly. Because of that, right now in some countries, for new, they try to make the same code for new and existing buildings, the same approach. But it takes a little time, because in the new buildings you rely too much on prescriptives, and the prescriptives are very important things. They came from experience, but many of our analytical work is just we model, get the results. So we are is not as tested as those prescriptives. For example, we have seen in many earthquakes that short column is always damaged. So it is damaged. But now we can model it, show it that in this case is not damaging. Let it be there in our buildings. Usually the authorities are a little careful, say, because your modeling, yes, good, advanced, but maybe your software, maybe the elements that are used is not capable enough to model these effects. So I think it's a little, we have a little, there is a little time before we use them very easily for the new buildings. But the guidelines are available, especially for tall buildings. For example, we have right now they are applying for the ordinary buildings. The tools are available and it's not a big deal, but just is the measure of the authority, the board committees, they think that it is time the engineering community is ready to apply for the new ministry. Can we perform linear static analysis if a existing building have torsional irregularity, or do we have to response spectrum analysis for that specific existing building? For linear static analysis, usually there are some advice on this. For example, they let to do the pushover on a torsionally irregular structure, but they modify the target displacement. And different codes, for, such as Eurocode and C, they have different approaches. For example, in some of the codes, they do, as you mentioned, a response spectrum analysis. So is a torsionally irregular. They do the response spectrum analysis, and then they find the ratio of the maximum top displacement in different ages. Is torsionally flexible or torsionally stiff, and therefore the based on the torsional properties of the building, the displacement at different location in the roof are different from that of center of mass. Then they use the same coefficient that, for example, at this age compared to center of mass, the displacement is 1.25. They use that multiplied to target displacement and push the building with this. Our approach based, if we do the research, there are many approaches that we can do. If we do evaluation based on a specific code, then we should use the recommendation of that specific code, which, as I said, many of course they have some recommendation. Dear Mr. Rudra, if I am correct, I think that's the final question for tonight.